Hello everyone, welcome back. We looked at simple one dimensional waves last class for expansion process, and we said that we have to look at it as if I have a flow, and if there is a wave and the wave is going like this, the induced flow will be, the induced flow part alone will be like this. If the flow is already having this big velocity, the induced flow should be added to it and it will be slightly lesser only this much will be the final velocity. This is what we saw last time. If it is an expansion wave, if it is a compression wave, then the induced velocity will be in the same direction. And I gave some statements like the wave will talk to the fluid and it will tell that there is empty space there, go that side, and it will keep going this side. That is what I said last class, right? And similarly, if it is a compression wave, it will tell there is less space there, come this side, and they will go along with the flow. Along with the wave, the fluid will go along with the wave if it is a compression. If it is expansion, it will go against the wave flow direction. Okay. Now we want to derive this in 2 dimensions. We are going to take the similar approach like we did for oblique shocks derivation, where we said if there is a wave, I am going to look at the normal component and how it changes. I am drawing an oblique shock picture here though. Okay, the arrow lengths are changing that way, and I am going to say that the actual velocity is this, and we have a observer moving along the shock this way, that with respect to that observer the flow field looks like this, right. Now if I combine that with the actual flow along a normal shock, which is this velocity, and it decreases to this velocity, with respect to that observer who is moving along this way with velocity v, he will see that the flow goes like this and then it is going to go like this. This is what he will be seeing. That is the idea, right. This is how we derived oblique shock relations. Now we will go and do the same thing for expansion wave, okay, where we will start with one wave. We already said last time that the waves cannot get together to form a strong wave last class. So now I am going to consider only one wave, they do not ever get closer. Okay. Now we will consider a similar situation. Incoming flow is parallel to my ground reference, okay, and we are going to split it into normal and tangential components with respect to this wave direction, okay. And let us call this as my w velocity, small w. Okay. I want 3 different variables for velocity. I am going to use u, v and w. I will have u here, v here, okay, and w is the total. The net velocity will be this. These are the components. This is how I am defining it. And now I have to tell something more about this wave. If a wave is traveling at speed of sound or almost equal to speed of sound in a flow which has a velocity direction like this, what will be its angle with respect to this velocity vector? What should it be? It should be same as your Mach angle. Why? This is how you defined your Mach cone, right. We had flow velocity this way, and so I just extended that line for this point. This is the direction along which the speed of sound will the sound waves will propagate at most, or anywhere inside this. It cannot go outside this. This is how we got to this mu. I am going to use the same kind of explanation here, and I am going to say a wave is traveling this way with respect to the flow velocity at velocity wave velocity equal to speed of sound, almost equal to speed of sound. I told this last class also, right. It is slightly less, infinitesimally less. We will take it as equal to speed of sound, and so it is going to have this angle. Okay. Now once I draw this angle as that value, immediately I can just translate that into here, because this is parallel to that line. This is also going to be mu. Okay. That is easy to tell now. Now once I draw this, now remaining things I just have to continue from here and say I am going to have a deflection. this is my final deflection. I am saying this, okay. This is the final deflection, and I am going to call this as d nu, because we want to integrate it later. I could call it d theta. Theta is already used for oblique shock. I will keep it as nu for this one. Okay. It so happens that Prandtl-Meyer function uses nu for several books. I will just keep that the same. Okay. And in terms of perpendicular to the flow direction, what should happen to this flow velocity? It should just increase across. Okay. It should just increase to some other value. It should be more than that u value, u plus du. That is what it should become finally, right. And the tangential component should not change. The way I have drawn it, it looks like it has changed slightly, but let us say this v and this v are the same. Okay. I have drawn it slightly, this v is slightly smaller. Let us assume that they are the same. Now, what we have to do is conservation of mass across this wave. Okay. I have to start conserving mass across this wave, and I am going to look at the component directions. Okay. Simplest thing I can do is I will go for v direction, very easy to work with v direction. Okay. V direction, I am going to tell that whatever mass comes in this way is going, the component of movement this way is going to be conserved that direction. The way I am going to use it, w times cos of this angle, right, w1, or it does not matter, it is w only, w cos mu. I am going to use this. This is going to be equal to, on the other side, what is this going to be? W1 plus dw. W is again velocity, remember that. Okay. That is the total velocity, times what is the angle I have to consider? This is the final w, okay, which is supposed to be w plus dw. I did not mark this. Let us say this vector has a magnitude of w plus dw. Okay. This vector length is w plus dw. If that is the case, I want to find the component with respect to this line. So, that is going to be cos of this mu plus this d nu. Okay. We have this expression. Now, all I have to do is just expand this, because I know I use this w1 here, just make it w, w1 or w are the same for me. Okay. W times cos mu will come out of this side, which I can directly cancel with the left hand side of this equation. Okay. So, I want to expand it and cancel that particular term. If I write it again, w cos mu is equal to w plus dw times cos of a plus b expansion, cos mu cos d nu minus sin mu sin of d nu. This is what I will have. I have this. Now, I have to try and rearrange the terms with a small limit. Okay. I am going to tell that this d nu is a very small deflection. Why? I have considered only one wave can affect only extremely small quantities, right. That is what we said last two classes, in fact, right. One single expansion wave which is almost isentropic can affect only a very small amount. Okay. So, the change cannot be very big, it has to be extremely small value. So, I can now say that the d nu is very small, dw is very small, du is very small, dp, dt, everything across this is all very small. Okay. They are all of the order of d nu if you want. Okay. Except for entropy, I am going to say it is approximately equal to 0, we will just force it to be equal to 0, because we are using isentropic implicitly when I say mu is the angle here. Okay. We will keep it that way. So, when I say limit of d nu tending to 0, what will happen? This cos of d nu is almost cos 0 is 1, okay. And sin of d nu, I will just replace this sin of d nu as just d nu. I do not want to make it 0, If I make it 0, there is no d nu in my expression, the whole thing will just get cancelled and dw will become 0. Okay, that is just a no use solution, we do not want that. So, I want to keep that d nu in there. Okay. So, when I do that, I will write it fresh on the other side, w cos mu w plus dw times cos mu times 1 minus sin mu d nu. This is what I will have. Now, I just directly see that w cos mu will just cancel with this w cos mu. Okay. So, I will just put 0 here equal to the remaining term will be dw cos mu. I will put brackets so that we know what we are doing. Now, w and dw were multiplied with cos mu already. Now, I have to take this and multiply with this term. So, I will have minus w sin mu d nu, that is one term, and then the other term is dw times d nu, which I am going to say is too small. Multiplication of two very small quantities, I will say that is very small. So, I have only this expression. Okay. Now, I will take one term to the other side and rearrange this. I will get dw by w is equal to, I have taken this term here and brought the w down here. So, it will become sin mu by cos mu, which is tan mu, times d nu. This is one relation. Okay. What does this tell me? If my d nu is positive, I am going to say that my dw is positive. My flow will accelerate if my d nu, the way I chose it, which is here, I have chosen it to be going below the horizontal. If it goes like this, then it will be positive. If I chose it d nu to be negative now, I give it a negative value, what will it happen? The flow vector will go the other side. If that is the case, automatically this expression gives me dw is negative, which means my velocity decreases. Okay. That is what I am getting here, which means that will correspond to a Prandtl-Meyer compression wave, okay, a single compression wave we are talking about, almost isentropic but compression wave. That is the answer you will get from that. Okay. Now, the next thing we want to do is get rid of this dw by w and keep only Mach number in there, because we do everything in terms of Mach number to simplify the expression. Otherwise, I need to know the exact velocity there and then work with that. It is more complex if it is do this. Okay. So, we will start from our energy expression. Okay. T naught equal to T plus W square by 2 Cp. This is how we started energy expression. Okay. And of course, I could start from another place, but I want you to get familiarized with this particular derivation. So, I will keep deriving this several places. Multiply with gamma r everywhere. Okay. Once I do this, now I can rewrite this gamma RT as a square. Now that a I will replace it in terms of w. Okay. That will be w by m square, right, because m is w by a. I can write it like this, plus now my Cp is gamma r by gamma minus 1. Okay. And I already have gamma r there, which will get cancelled. Gamma minus 1 will go to the numerator, gamma minus 1 by 2, and this is what I have. Okay. Now, I could have derived it from somewhere else, I will just keep it this way. Okay. Of course, you guys know that directly this can be rearranged to the form T naught by T equal to 1 plus gamma minus 1 by 2 m square, right. This is the same derivation we went through to get to here. Now, I want to keep things in terms of w's. So, I will not go that direction, I will keep it this way. Okay. I did this specifically so that you will remember this particular formula I wrote here. Okay. Now, I will go gamma r t naught. Now I have to group them in such a way that all the w's are out, 1 by m square plus gamma minus 1 by 2. I have this form here, I have to get here dw by w. If I take this expression and differentiate this with respect to some any variable, then I will get a dw from there. So that is what I am going to do, I am going to differentiate this expression, okay. And I know that it is almost isentropic problem, so my t naught does not change, gamma r t naught does not change for me. So when I differentiate this side of this equation, this is going to be 0, okay. So it is going to be 0 equal to, when I differentiate this term I will keep this bracket constant, okay. So that is going to be 2w dw times this whole bracket 1 by m square plus gamma minus 1 by 2 plus differentiation of this term multiplied by w square into 1 by m square differentiation, m power minus 2 will be minus 2 m power minus 3. So, it will be minus 2 by m power 3 dm. Yeah, and gamma does not come in at all, gamma is a constant anyway, so that does not come after differentiation. So, this is your expression you have now, okay. Now, I want to rearrange this a little bit. I am seeing that I want dw by w, that is the goal. How will I get dw by w here? I will multiply and divide by w here, that will give a w square dw by w, and here I have a w square already, but I have a dm by something. I will rearrange it such that I have a dm by m here and dw by w here, okay, not very difficult to do. I told you already, gas dynamics people like this d rho by rho, du by u, dA by a, like that, it is dw by w and dm by m, okay. We will rewrite that. I will keep the 2 inside, I will just pull out w square by m square from the whole expression. I am going to have 2 dw by w times this plus, actually it will be minus 2 dm by m, this whole thing equal to 0. This is what I will have. Just follow it, if I am making a mistake, I am doing it out of memory and not from my notes here. Okay. There is a mistake, you should tell me. Okay. I am having this expression here. Now, I am going to say this is equal to a square, and which is equal to gamma r t, which will never be 0. So, only this flowery bracket thing must be 0. Okay. So, now I have an expression for dw by w. I will rewrite this thing as dw by w is equal to dm by m divided by 1 plus gamma minus 1 by 2 m square. Okay, I think the 2 gets away from there. Okay. So, and we derived one expression before this. I am missing one particular derivation from here. Okay, I will write the other expression here directly, tan mu d nu. This we derived here from this board. Okay. We derived this, I am just putting that also equal to that. Now, I have to go back and look at my mu function. Okay. I am going to look at it this way. What is tan mu? Actually, I don't need this at all. Directly I can tell you tan mu. What is tan mu? Sin mu by cos mu. So what is it? Okay. Sin mu is what? Mu is sin inverse 1 by m. So this is 1 by m. Cos mu is square root of 1 minus 1 by m square. Okay. Now I have to divide one by the other. What will I get? Tan mu, I will just rewrite this, it is easier, m square minus 1 by m square, okay, which will be 1 by m outside, that will cancel with this. So I will just have 1 by square root of m square minus 1. Okay. Now I will substitute this in this tan mu here. Once I do that, I am going to have an expression dw by w equal to, oh, I do not need dw by w, I want to write expression for d nu. D nu is equal to, I will write it as that 1 by square root of m square minus 1, I will take it to the numerator here, I will have square root of m square minus 1 dm by m divided by 1 plus gamma minus 1 by 2 m square. Okay. This is some expression which is just nu is a function of Mach number. Of course, it is also a function of gamma, it is mainly nu as a function of Mach number. Okay. This is one important expression we have, but this is not easy to use as of now. Okay. And of course, the actual thing you need to do to find how much will be my Mach number is the inverse problem. Okay. If I deflect my streamline by so much d nu, how much will be my new Mach number? That depends on dm, m plus dm is my final Mach number, and that is not very easy to get from here. So of course, you have to integrate this, okay, then I will get nu as a function of m here, okay, that is what I will end up with. So how will I do that? I will not actually do the integration, I will just go to mathematicians, but just to make it look like I am doing something here, I can just go for, now this looks like, I will put a 2 and a 2 here, okay, I multiply and divide by 2m. Now this is your d of m square, okay, this is your d of m square. Now every other function is just m square, okay. Now I can substitute x equal to m square and integrate this. I will not do the integration, I will just give you the final expression. Now before I integrate, I have to do one more thing. When I put d nu integral, I want to put limits for it. What limit should I use? Okay. For this d nu, I have to give a lower limit and an upper limit. Where am I starting from is the basic question. Okay. Now I have to find out where I am starting from. Not an easy thing to do. I will go back here. We know that all the expressions here will work only for supersonic. Why? Somewhere along the line, I said that I have a square root of m square minus 1. Okay. It cannot go complex. This whole derivation assumed that my Mach number is more than 1, otherwise I cannot have a mu angle itself. Okay. Sin inverse 1 by m is not valid for m less than 1. Okay. So I am assuming that it is supersonic already. Okay. Which being said, what is the least point where this function will work? M equal to 1. So I will pick that as my reference currently. Okay. So I am going to say nu of m equal to 1 is one side, and the other side will be nu of whatever m, whatever value of m. Okay. Now this is the way I will integrate in nu. I do not know the values yet, we will figure out what to do. Other side I am going to integrate from 1 to m square root of m square minus 1 divided by 1 plus gamma minus 1 by 2 m square d of m square divided by 2 m square. This is the function I have. Now let us say I know how to integrate this. Okay, you can just tell directly that 1 plus x square kind of form will give you tan inverse function. Okay, it's not just a simple thing because it's also having other term. Okay, so if I go and ask the mathematicians, they are going to tell me that this integral with the limit substituted comes out to be square root. Okay. Now I have to do one more thing on the left hand side. After that I will put a big box around this. Okay. One thing I have to do is I am going to start with a reference, and at the reference I am going to set my nu to be 0. I am going to say this is defined to be equal to 0. Okay. Nu at m equal to 1 is defined to be 0 for me. My Prandtl-Meyer angle at m equal to 1 is defined to be 0. Okay. Once I do that, now the remaining thing will be just nu. Nu of m is equal to this. Okay. This is a function which is purely a function of gamma and m only, and I can tell you for every Mach number some value called the Prandtl-Meyer angle. This is called the Prandtl-Meyer angle. Okay. I will write that at least once. Prandtl-Meyer angle. Okay. Now, how will I use this is the next question. Okay. Now I have this, and I will tell you that this particular function is not very easy to calculate at the calculator every time. So this is tabulated. Okay, it is also available in graphical form. That is what was more popular long back. Now tabulated is easy enough for us to use. Okay. It is tabulated and we can use that. Okay. Now how will I use this function to calculate anything in my flow? For that I have to get a practical feel for what this means. Okay. So let us consider one particular specific problem where I am having flow parallel to a wall, and it is m equal to 1 here, and it is bending by some angle, and its final Mach number happens to be m. Okay, let us say this is m1 and I will call this m2, that is easier to understand. Okay. Now I will get a new value for this as 0, and what will I get for this value? I will get a nu of m2. Okay. Now since we integrated from this point all the way to there, and we already said that d nu is the small change in the streamline direction caused by that one individual wave. When I integrate, what I am doing is I am integrating over a whole bunch of waves. Okay, a whole bunch of waves. We said the expansion fan contains a lot of waves. We typically represent it by first wave and the last wave and probably a middle wave. That is all we do. Right? But it is actually a whole bunch of waves inside, infinite number of waves, and if I put that in here, that is going to be somewhere inside. Okay. This is a whole bunch of waves. This is your fan, expansion fan. Okay. And now if I tell that I am integrating over all the deflections of streamline, what am I going to say? I am going to tell finally that this difference between these new values will be equal to my total deflection of streamlines. Right. So now I will mark this as theta, the total deflection. I am going to say theta equal to nu of m2 minus nu of m1. This is a very useful formula. I will keep it this form, and then now I will use this for the specific case nu of m1 is 0. That is how we defined it. So, theta becomes equal to nu of m2 for this special case of this problem, okay, and the flow will go like this finally. This is what happens here. Okay. There are some set of expansion waves that are going from this corner all the way out like this. Okay. What if my m1 is not 1 but some other value? How will I think about this problem? For that, I will draw a different figure. I will just draw the same thing similar to what I have drawn before. This is having a deflection of theta, and this is having some m1 greater than 1. But if you have a feel for this problem, after that you can apply it anywhere. So, I am just trying to give you the feel for the problem. Okay. And it is of course going to have some set of expansion fans here, and then the final vector direction will be this, and the velocity magnitude will be longer. Of course, the velocity vector should be longer. It is accelerating the flow, and this is what you should have. To solve this problem, I need to find nu of m1, nu of m2, and then the difference must be equal to theta. I gave away the formula already. But to think about physical feel, I am going to imagine this problem of, I have some other direction here. I am going to imagine a wall like this, and I will put dashed line for this wall because it is my imaginary wall. It is not really there in my flow field. The actual wall is something like this, let us say. I am going to imagine this wall starting from m equal to 1, going to a case where it is becoming m1 equal to that particular value. Let us say it is 1.5, 1.4, whatever number is going to that value. I am starting from m equal to 1 and it is turning to go to that particular value, and after that it is again turning at this point to go to this value. Okay. So, if you imagine this in any problem, then you will never make a mistake in this. Okay. Prandtl-Meyer angle corresponds to, from here how much should I turn the streamline to go to that particular Mach number. Let us call this m2 again. Okay. From here I have to turn by this whole amount to go to this Mach number. I have to turn a little less only up to here to go to this Mach number. That is all it is, right. And by the way, the Prandtl-Meyer function is a monotonic function. It is not going to go up and down, it just keeps on increasing. That is one more important thing you should know. Okay. But as it goes to very high Mach numbers, the number does not change, it is going to asymptote to a particular value. Okay. But this is how you have to think about it. If I am thinking only about this problem and I have another change here, say there is another change and there is some set of waves here, set of expansion waves again, the flow is going like this. Let us say I did not do this problem already. How will I think about it? I am going to imagine that wall like thing here, that dashed wall. I am imagining this and I am going to say this is m equal to 1. From here it is turning by so much. How much? Equal to nu of m2. Okay, and it came to here. Now I am telling it has to expand more. How much more? By that small angle. If I think about what should be the Mach number here, I am going to say I start from m equal to 1 and I am turning the whole amount here. This turning is more than this turning. Okay. When that is happening, I can tell that this will have a higher Mach number because I know nu of m is a monotonically increasing function. Okay. So, and what will be the difference? I stop here, I continue to move over here. So, I can tell that theta equal to, I will call this m3 now. Oh, I named it theta. I call this theta 2 and I will call this theta 3. I will put theta 3 equal to nu of m3 minus nu of m2. Okay, something like this. Basically, it is just coming down to the deflection is equal to the difference in my Prandtl-Meyer functions for those Mach numbers. Only one caution in this whole thing: the Mach number can never be less than 1. Okay. If it is less than 1, I cannot use this whole analysis because during the analysis I assumed that I have supersonic flow. Okay. So, I cannot use that analysis if that is the case. Now, I will give you different problems to think about, all this time I have been thinking about corner. I said this is a corner, it is typically called a sharp corner. Okay, it is a sharp corner expansion. If this is the case, then I will have expansion waves coming from that point, the corner point, all concentrated from that point, it is coming on. If that is not the case and it is more like this, say the same angle deflection, then I can imagine this wall as a whole sequence of small deflections. For every tiny deflection, there will be one expansion wave. Something like this. For every tiny deflection, there will be one expansion wave. Okay? And now the flow is going like this, it is going to slowly turn to finally become that. In both these problems, I can use the same function. Okay, the delta theta is equal to delta nu, I can use that. Okay. Now the only other thing I have to think about, how will I relate this and this? If I go zoom into this region, if I go really zoom into this region and just see what is happening at that corner alone, there will be a point where it will become a radius, right, mechanical machining, whatever, it will always be this form. If I zoom into it so much, it will finally end up here. Okay. And if I zoom out of this problem, this radius will become very small change and eventually it will go look like this. Okay. This is what they call a smooth corner, the change is slow, and this is a sharp corner or a sudden corner, okay, sudden change in angle. These are all expansions. How did we define expansion? The wall moves away so that there is more space for the streamlines. This is an expansion. We already did compression, and there the wall will move into the streamline path, so that will become a compression wave. Okay. Now I just have to give you one more picture. This particular picture will be useful when you are thinking about solving problems. You will always never have a case where it will be always wall at the bottom. You may have wall at the top. So how will I imagine that? I just have to flip this picture upside down. Okay. I will draw a wall like this, and now I am going to say this is m greater than 1, m1 greater than 1, and it is becoming m2, which will typically be greater than m1, right? There is no other case, I do not need to write it also, you should know this. And there is going to be expansions this way. How will I imagine that m equal to 1 point here? M equal to 1 point I have to imagine. It is going to come from the top this side. That dashed line wall I am going to draw here will be coming from here, m equal to 1, it is going to turn, deflect this way and come to m1, which is greater than 1, let us say it is 2. And then if I expand more, it may go to 3. The total expansion from m equal to 1 direction to here will be some value, and then from here it is going to expand more. The difference in the nu will be equal to that deflection here totally. Okay. This will help you understand the problem, so you will never make mistakes in this case. Okay. And of course you can always make it a smooth corner or a rough sharp corner depending on the problem, it should not change anything. Now we will just go for the animation there. This is the piston analogy problem we are showing here. We are having a piston similar to your compression wave piston analogy we did before. I am having a piston and it is expanding out at a constant rate, and when it is expanding, the first expansion wave is going in there, this is the first expansion wave, while this is the final expansion wave, which tells that after that the velocity is constant, nothing more changing there. And this is your high pressure gas which is slowly expanding because this wave is going and telling there is lesser pressure here. In fact, I have drawn only 2 lines here. Ideally I should draw infinite number of lines here. Yeah, there are so many waves here. This is the first expansion wave and this is the last expansion wave. Okay. And we already did the pressure plot of what this cross section will look like, pressure variation, last class. Okay. So this is this case, this is 1D problem, but we did all 2D expansion fan. We will go look at that next. Okay. Now similar to our piston analogy for 2D, from 1D to 2D. If I have a piston cylinder arrangement and it is moving across horizontally in a constant velocity, and I am seeing what is happening to the particles inside, the piston starts moving somewhere here, okay, somewhere this point onwards. We will run it again. You are seeing that as it goes, whatever is happening inside is same as what we saw before, okay. And this is your first expansion wave going that way, that time trace of the first expansion wave going that way, and this is the time trace of the last expansion wave that is going here, and then this is your time trace of the piston, which is equivalent to our wall in this case. So, I am going to have an expansion fan. This is a region where there are so many expansion waves, and the expansion waves are more and more apart as time goes. So, this whole region is expanding out like a fan. Okay. Also shown here is the streamline path for this two particles here. In fact, this is like exact particle tracking thing. We just picked two particular particles here, and we are just tracking what it looks like in time. And what you are seeing is the one particular particle, this particular particle you are tracking is here in that case, and it is now here, it is now here, it is now here, it is now here, like that. If you are tracking that particular particle, that is the lower streamline here, it is coming here, it is starting to turn somewhere around here where the first expansion line touches that. After that it changes, and then it comes to a constant rate after that, it is becoming parallel, it is moving parallel to the wall, okay. And we are also tracking another particle here, some other particle, some other streamline, slightly higher streamline, that is starting almost close to that one, and it is coming here, and it is getting accelerated, and it is slightly higher, so it is experiencing the expansion for a slightly longer time. It is going through the expansion like this, okay. It is stretching inside, and then the gap is increasing here, and finally it will come out from here, and then you can again see the particle here, particle here, particle here. It is just moving at a constant velocity parallel to the wall, if you imagine the 2D case, okay. It is just a constant distance from the piston, which means the relative velocity is 0. It is moving same velocity as piston in this region. In here the velocity is 0, the top region, and inside here the velocity is increasing from 0 at this point to velocity of piston at this line. After that it is all velocity of piston all over here. That is what is actually happening inside there, okay. This is just two different ways of looking at things, okay. Once this is given, I will go to another problem. I will go back to the board. I will tell another problem where I have a Mach number greater than 1 flow, and it is having a smooth compression corner. If it is having a smooth compression corner, then of course the same thing like expansion will happen. For every small change there will be one compression wave. There will be one compression wave coming for every small change. Now I am trying to pull you out of this thinking of there will always be a shock, right? And I am going to say that for very small changes, the wave that is produced is very weak. You can consider it as a very weak oblique shock, or I will just consider it as a compression wave which is almost a Mach wave. I will think about it that way. If I think about it that way, now I am going to say there is a Mach wave, okay, and there is next Mach wave which is telling that there is a small change, some other increase in angle, another increase in angle, another increase in angle, another increase in angle. So now I am going from here continuously changing the other direction. How will I know that now my flow will turn this way? It is a compression, my d nu is now negative. By our convention, going this way is positive, going up is negative. When my d nu is negative, my dm is negative. From that formula we wrote, the formula is still here, this one, okay. If my d nu is negative, m is positive always, so my dm will be negative, okay. So I can tell that if my wall is going in, then my Mach number will decrease, okay, and that is your compression phenomenon. It is going to have a whole bunch of compression waves coming together, and of course we won't worry about what will happen when they come close to each other. Okay, they eventually collapse to form a shock, oblique shock finally. Okay, we won't worry about that part right now, we will deal with that after some days. Okay, and it is going to go through this. This particular problem, very close to the wall of this particular smooth compression, I can still use Prandtl-Meyer angle to solve this problem. I will get the Mach number here exactly that. Okay. But when these things interact, similar to what we did last time, when oblique shocks come and interact, they may form a slipstream kind of stuff. Here also there will be some slipstream forming here. Okay. There will be a slipstream forming, not just one slipstream, probably there are a whole bunch of slip region might be formed out there. We will just ignore all that for now. Okay. I will show you pictures of that if needed. Okay. And so with this, I can now start solving problems. Okay. Like I can just tell what will be the Mach number, I can start predicting Mach number values. Okay. Now just to have a feel for these numbers, I will tell you the limits for these numbers. We just have a few minutes more. So what will happen, I have the expression here. If I set my Mach number tends to infinity, then I can easily tell this term is very easy to work with. This is going to go to infinity, and I am going to tell tan inverse infinity is pi by 2, which will become 90 degrees if I convert from radians to degrees. But this term, this is going to have some number. Okay. But it's still tan inverse infinity, that I do not need to worry about, that is going to be pi by 2. But square root of gamma plus 1 by gamma minus 1, for gamma equal to 1.4, this is 6, right, we did this long back. Okay. You guys just get used to this number. Okay. Now I have square root of that. So it is going to come to some particular number, it will be 2.236 multiplied by pi by 2. Now that I have to convert to 90 degrees. Okay. It is going to go to that. What will that number be? Okay. Let us say I am going to write that m tending to infinity case, nu tends to square root of gamma plus 1 by gamma minus 1 minus 1. Remember that there is a minus pi by 2 there. Okay. This whole thing multiplied by 90 degrees. I have converted it from radians to degrees now. Okay. Now let us look at this number for 3 different cases. Gamma equal to 1.3, this number is 159.2 degrees. Gamma equal to 1.4, this number is 130.5 degrees. Nu equal to 1.67, oh sorry, I put nu here, it should be gamma here, and that is nu. This is gamma. 1.66, this value is 90 degrees. Okay. This is what we are having. Okay. What does this mean? Even if I accelerate my flow, say my flow is coming with m equal to 1 here, and I turn it straight back to 180 degrees, my flow has to turn around fully. The flow does not follow the wall anymore. That is what it says. Okay. If my gamma is 1.3 case, if I have a case of gamma equal to 1.3, then it is going to turn by that 159 degrees alone. That will be something like this. My last streamline near the wall will separate from the wall and it just gets out here. This is what will happen. Okay, this angle, not there, sorry. The angle is angle deflection for the streamline. So this is the streamline going to turn like this. This is your 159 degrees. This is what you will get. If I have the same thing for gamma equal to 1.4, I will draw another picture. Then this is going to go for 130 degrees. 130 degrees here. This deflection is 130 degrees. And inside here, what will it be? There is nothing, vacuum. As far as our simple gas dynamics goes, this region there is nothing, it should just be vacuum, which breaks down, our assumption of continuum breaks down at this boundary. So at m equal to infinity we cannot use this analysis. Okay. Just know that this gives you these numbers, but these numbers are not valid when I go m equal to infinity. Okay. We will pick up some specific numerical examples next class onwards. See you people next time.